Another unit that we can deal with, this is the SI unit for amount, the mole. It's the second and more fundamental thing to understand about the mole is how to get its specific value. Now, what is a mole? Now, a mole I like to think about as a dozen. What is a dozen? Well, it's 12 of something, right? The mole is like a chemist's dozen. It tells you an amount of something. Now, when we're trying to think about the biggest problem in chemistry, it's moving from the subatomic realm to the real world, the macroscopic realm. How do we connect something like an AMU to a kilogram? It's really hard. 1 AMU is somewhere around 10 to the negative 27 kilograms. We can't measure that mass in the lab. So how do we connect it? And the answer to that is the mole. This handsome guy right here. Avogadro was the first scientist to actually investigate the actual number of particles in a sample. Amedeo Avogadro was from Italy. He was born in the late 1700s in Italy. He went to the University of Turin, and when he developed his idea of the mole as a way of counting atoms and relating it to mass, people actually didn't take him seriously. We're going to see that repeated a lot in this class. And it wasn't until 4 or 5 years after his death that people really started to understand, wow, this was important. The mole is how we connect the laboratory scale to the subatomic scale. And the exact value of the mole is equal to the number of atoms exactly in 12 grams of pure carbon-12. Why carbon? Well, me being an organic chemist, I'm biased to carbon, but think back way back when Avogadro was doing these experimentations with determining the mole. Carbon was readily available. It was often used already in combustion reactions. And so a lot of people were already working with carbon. And carbon-12 is the most abundant isotope of carbon. And there was just a lot of it around. The other isotope of carbon that is naturally occurring is carbon-13, but it's really only about 1% of carbon is carbon-13. There is such a thing as carbon-14 dating. However, that is very, very small amounts, and so that's not in this discussion or usually ever in calculations with finding any sort of average atomic mass of carbon. So most abundant element, carbon. Most abundant isotope of carbon, carbon-12. So exactly 12 grams of carbon is equal to 1 mole. And Avogadro determined that that is 6.022 times 10 to the 23rd carbon atoms. This is where we get the value N sub A, or Avogadro's number. Avogadro's number is 6.022 times 10 to the 23rd particles per mole. I'm going to change it to particles here. The reason for that is so that we can understand this isn't just related to carbon. Yes, it was based off of carbon because of the reasons we stated earlier. However, it doesn't mean that it only applies to carbon. It applies to anything. So you could have a mole of donuts. Yeah, I want a mole of donuts. Screw that 12. I don't want a dozen. I want a mole. I want 6.022 times 10 to the 23rd donuts. That's a mole of donuts, right? We can do any type of particle. It can be atoms. It could be particles like protons or electrons. It could be a molecule. It could be something like CH4, right? I want a mole of CH4, the molecule, methane. That would be 6.022 times 10 to the 23rd molecules of methane. So this number is very, very useful. What it also does for us is it gives us a new conversion factor between particles and grams. And that mole is that idea that links us into the atomic realm. The AMU, the atomic mass unit, can now be defined as a ratio. 1 AMU will be equal to 1 gram per mole. That is highly useful for us because now we can use all of those AMUs on the periodic table, the average atomic masses, and say, okay, we just calculated chlorine's atomic mass. And that atomic mass was 35.45 AMUs. But what we can do now is take that number into the lab. It's so exciting, 35.45 grams per 1 mole of chlorine. So that is very, very useful for us. Just a couple of practice calculations so we can see it. Calculating the number of copper atoms in 2.45 moles of copper. How we would set that up, 2.45 moles is our given value. We would use Avogadro's number. Now remember, when we are converting between one unit to another, we always want our desired unit in the numerator and our current unit in the denominator. What that does for us is it allows us to actually cancel or cross cancel between the numerator and the denominator, and our current unit, which is moles, and our desired unit, which is atoms. And now looking at Avogadro's number, I know the 6.022 times 10 to the 23rd atoms goes in the numerator and 1 mole goes in the denominator. This conversion factor, again, we never want to use that for our sig figs. Think about that conversion factor as an infinite number of sig figs. So the value we want to look for is our measured value, our given value for our sig figs. We have 3 sig figs here. And so in our answer, we should have 3 sig figs. This is a multiplication question. So we're multiplying 3 sig figs by an infinite value of sig figs. 1.48 times 10 to the 24. Don't forget your unit, copper atoms. There's our answer, 3 sig figs. We can go the other way and calculate from grams all the way now to number of atoms. Very, very cool. Let's go back to our periodic table and get that helpful, useful information piece. Where is it? There it is. Copper, 63.55 for its average isotopic mass, which means 63.55 grams per mole. So let's go ahead and start out. We never want to start with a conversion factor. We always want to start out with our given measurement, 3.10 grams of copper times, well, I want to get to atoms. How do I get to atoms? Through the mole. So 1 mole of copper over 63.55 grams of copper. I can keep going with my conversion factors here. I want to get to particles or atoms, 6.022 times 10 to the 23rd atoms of copper, Cu, over 1 mole of copper. Notice how, again, as chemists, we like to abbreviate. MOL is the abbreviation for mole, because why write 4 letters when you could just write 3? Make sure that your units cancel. Grams cancel, moles cancel. We're left with atoms. Lovely. So we would do that calculation. 2.94 times 10 to the 22 copper atoms. Now, fun fact, the original 1982 or earlier penny was actually mostly copper. Now it's not. Now it's copper plated and it's zinc on the inside and some other alloys. But if you have any original, before 1982 copper pennies, they averaged weight 3.10 grams. You now know, party fact, 2.94 times 10 to the 22 copper atoms are in that penny. How cool is that? You're gonna dazzle your friends the next party. 3 sig figs, just to emphasize that sig figs are always important for us in these calculations. Again, conversion factors, infinite number of sig figs. Don't ever look at those. Think about them as an infinite value of sig figs. They are an accurate number. So just look at that measured value. Just a brief introduction. We're moving into energy, chapter E. E.6 is what we're really going to be looking at here. Overall, just a couple of definitions and a couple new conversion factors in order to be able to work with those throughout the next couple chapters. Energy is in the universe is conserved, and all matter has energy. These are laws of energy and laws of thermodynamics that we have. We go into those more in depth in Chem 150. So if you take Chem 150, you're going to see this overarching idea again. What I would say just for right now, we'll use some of these factors once we get into movement of particles in chapter 10. Right now, what would just be important is some definitions and seeing what parts of physics do we bring into chemistry. The 2 main ones are looking at the idea of kinetic energy versus potential energy. Kinetic energy is associated with movement. So this right here, the actual movement of the weight after we throw it off the building. We have a calculation with that. This should be squared. Kinetic energy is equal to 1/2 mass times velocity squared. So the mass itself contributes to the kinetic energy and the actual velocity of the object. We will again see this calculation in chapter 10. Potential energy is the energy associated with position or composition. We can think about this as bonds, bond energy, also sometimes called chemical energy. We'll get into bond energy a little bit once we start building up our molecules. A lot of bond energy is not utilized again until we get into thermodynamics, which is Chem 150. Now, energy can be converted from one form to another. So chemical energy or potential energy can be converted to movement energy or mechanical energy. Such as solar energy can be used to be converted into mechanical energy. So we can interconvert between these two. Energy cannot be created nor destroyed, but it can be transferred. Just like our law of conservation of mass, we have almost the exact same law, the law of conservation of energy. In terms of some energy terminology, when we get into the first law of thermodynamics, that all matter possesses energy, we will be able to again see not only can we change from kinetic to potential, we can also change from a reaction or a system to the surroundings. So a system is really what we study, the actual chemical reactions that we have. And we can see that around us are called the surroundings. That's where we are. We're not part of the reaction, hopefully. We might get it on us, but we are part of the surroundings. And so what the biggest idea here is that the system and the surroundings can exchange energy all they want. Most often what we see is thermal energy, right? We can see that reactions could heat up. That's them releasing heat to us. We could see reactions cool down. That is the reactions taking heat from us. And so they get colder. Now, when we think about the universe, that is everything, the system and the surroundings. Again, we won't discuss the universe until we get into thermodynamics a little bit more in depth next semester. What we want to know is that thermal energy, the direction of heat flow. Heat is a type of energy, it's a thermal energy. And it's one of the most basic types of energy that we will see in this semester. Endothermic, if you think about that root endo, think about in. So I want to think energy in. Endothermic reactions take heat from the surroundings into the system. This is normally when we, the surroundings, feel a decrease in temperature. We feel the reaction getting colder. That's not that the reaction is releasing heat and getting colder. It's the reaction is taking our thermal energy and it's utilizing it in some way, shape, or form, kinetic energy. And so therefore, the surroundings are actually feeling that temperature get colder. Exothermic, we can think energy out, exiting the system. Heat is transferred from the system to the surroundings. This is when we feel things get hot. There are reactions that are endothermic or reactions that are exothermic. Most reactions fall into one of these categories. Very few reactions have an overall thermal energy change of 0. They might be very, very small that we might not feel them, such as dissolving salt in water. That process, we might not see any change in the temperature because it's so small. But dissolving salts in water, specifically sodium chloride, potassium chloride, and a metal with a halogen. We'll talk about all of our periodic table stuff in a little bit. Most of those are endothermic. But when we boil pasta, we just throw the salt in and we don't think about it. But in reality, very, very tiny change, very tiny, something that we probably wouldn't be able to measure in our kitchen. However, still good to know. What we get from energy units are our energy conversion factors. Most often in chemistry, we will use the joule. The joule is the amount of heat that will change the temperature of 1 gram of water by 1 degree Celsius. All of these conversion factors, whether you're dealing with calories, the kcal, which is our dietary calorie, or joules or kilojoules, all of these conversion factors will be given to you. When I'm looking at conversion factors, I don't want you to memorize them. There will be a few things that I want you to memorize. Prefix multipliers for one. So the kilo, I want you to remember. We'll use it a lot. This one, though, you should know. Kilo as our prefix multiplier. 1 kilo, and we'll just use joule, is equal to 1,000. It's that 1 to 1,000. And so if you have to review those, go back over our SI units and review or introduction video. Not required if you've taken this class before, but if you're brand new, that's why it's required in the lab.